Greetings, traveler. So, hi, it's episode, what is it? I lost count. 11. I just wrote it on the little card. It's 11, and we're into April now, which means it's almost time for what we at our college call the spring holiday. That's right, our school, who will remain nameless for reasons that'll become apparent in a minute. We love spring so much, we actually make a 4-day holiday weekend out of it. Now, I know what some of you are thinking. Hey, isn't this weekend also? See, now, the college I work at, we're a very progressive, multicultural institution, and we would never, ever cater to just one group of folks. The fact that this religious holiday is coming up this weekend is just coincidental. Even though every single year I don't do it. They arrange the academic calendar and say, okay, the college holiday is going to be this weekend. Right. It's spring, Easter is that weekend. God, every semester. Actually, I think we call it, I called it a college holiday a minute ago. Actually, they used to call it that too. I think this semester we're calling it the spring holiday. Spring holiday. It's my favorite thing is watching our college try to figure out what to call this holiday without calling it the thing that we're really doing it. I think actually once upon a time they did have it as Easter on the academic calendar. But I'm guessing somebody complained or somebody said, hey, maybe we shouldn't do this. Something probably happened. And yeah, they've been trying to call it something else. And at one time, I remember they actually called it spring break because back then what you think of as spring break were called faculty work days because that's really what they are. So yeah, on the look at the academic calendar, it looked like we were taking a spring break, with like 2 or 3 weeks left in the semester because Easter's usually at the end of April, and we were doing it on a Friday and a Monday. One of those days you wouldn't have class anyway because we don't do Friday classes, or a lot of them. So yeah, stuff like that is why I decided a long time ago I didn't want to go into administration. I don't want to talk like an administrator. I don't want to think, honestly, I don't want to think like one. It's just, and again, I'm not saying, in case one of you is watching, I'm not saying that our administrators are not intelligent people, just like I'm saying our elected officials who probably legislate all those weird rules that we have to follow aren't intelligent people. Just like I'm saying the lawyers that represent our school and the insurance companies that represent our school, they're not unintelligent people. But when you get them all in the same room together, it's like, for breakfast, I like eggs and bacon and grits because I'm Southern, and orange juice. I don't want them all in the bowl together. It's just nasty. Although I'm sure KFC is probably working on that, right? Hey, speaking of KFC, because I'm in a kind of a chatty mood, and if you don't, just skip ahead if you don't want to hear it. It's fine. I don't mind. I do it to Mark Maron all the time. Yeah, Mark, you're old and you have a record collection. Just get to the interview. Yeah, I don't know if anybody's seen, I've been seeing it on Hulu a lot, these KFC commercials where they show you their chicken strip things or whatever on one side, and they show you the competitor's chicken, which looks a lot like a McNugget, on the other side. And at the top it says, which one would you want to feed your kid? I'm thinking, aren't you the people who sell bowls? And didn't you just try to sell me something called a double down dog? You don't get to give me parenting advice, KFC. I'm sorry. You or the other companies that seem to share a restaurant with you, especially not the one that sells the tacos. How funny would it be if the ad you just saw for this was Taco Bell or KFC? Even better yet, as I'm saying KFC, the little ad pops up as it goes past the yellow line. Taco Bell or KFC, Pizza Hut. Fun. All right, so start off with general one. Let's get this show going. It's a nice day outside, and I'm going to go for a run. Just run. For the general one, guys, we're going to talk about the relationship that the periodic table has with electron configurations, because it's a really, really handy thing to understand when you're trying to figure out electron configurations for atoms. Because by now you know that the electrons arrange themselves around an atom in a certain sequence. You fill up the 1s subshell, then the 2s, and so on. And there are a couple of different memory aids sometimes people use. There's one you may have heard about if you took a lower level chem class, but it involves you taking the n's in a column or a row, and you put the s's and p's in another column and a row, and you have these diagonal lines. I don't like that one. For one thing, I can never remember what's in the column and what's in the row. And if you need a memory aid for a memory aid, it's not a very good memory aid. If you can't remember the memory aid, it's not a very good memory aid. Plus, all it tells you is this order of the subshells. You know, 1s, 2s, 3. But if you understand how the periodic table works with, or is linked with electron configurations, it's a lot better way to figure out electron configurations. All right, so there we go. Here we go. So initially, when you're taught the periodic table, you're probably taught about Mendeleev and how he grouped all these guys together by similar properties. And there's periodicity stuff that you heard about. But you know, we've tweaked it a little bit since Mendeleev's table. And one of the reasons that we tweaked it, not just because we discovered more elements since the late 18th century, but we've had a better understanding of the atom. And you know, the reason that everybody in group 1, the alkali metals, have similar chemical properties is because they have similar electron configurations. So for the most part, the periodic table is built around electron configurations. And with that, you can actually come up with a way to, I call it a memory aid, but I guess it kind of is, for lack of a better term. So basically, the way it works is you take your table and you split it up into 4 blocks. The first 2 main group elements you call the S block. The transition metals we call the D block. The remaining main group elements we call the P block. I know it starts to sound like prison. And the lanthanide and actinide series, the inner transition elements, we call the F block. So to get that filling order, starting with the lowest subshell, the 1s, and working your way across, you basically follow the periodic table down row to row, or period to period, if you want to use the more technically correct term. Whenever you go through the S block or the P block, your N is equal to whatever period you're in. Actually, oops, just whatever period you're in. When you start to go through the D block, the N is equal to your period / row minus 1. And when you go through the F block, when you get down to the last couple of rows, the N is equal to your period minus 2. So when you do that, now I should back up a minute. There are a couple of minor exceptions to this, because it's not 100% based on the periodic table. But the one you see right away is when you get through row 1, really helium should be, if it was 100% electron arrangement, here helium should be over the alkaline earth metals, because like those guys, it ends in S2. It's just one S2. But it behaves more like an inert gas. It is an inert gas. So we decided to move it over to group 8. I say we, I missed that meeting. Also too, the F block, if it was 100% based on electron configurations, it would actually include lanthanide and actinide and actually come right after the group 2. I think there are some versions of the periodic table where that is true, but most of them, 57 and 89, are shown as a transition element. But it turns out that even though we predict that 57th and 89th electron to be in an F subshell, experimentally it seems to spend most of its time in a D. So if you follow atomic number, remember that the F block should start here. For other reasons, this actually went over. But other than that, I mean, if you just work your way down row to row, after you go through row 1, it's supposed to be 1s2, which again isn't that big of a like I said, it's a minor exception, because with enough practice you realize that every atom starts with 1s2 except hydrogen, since this only has 1. But then you go through row / period 2. I know I keep saying row, it's one less syllable, right? It's 2s2, 2p6. You go through period 3, you're going again the S block and the P block. So it's 2s2, or sorry, 3s2. Think about what I just said, not what I'm currently saying. 3p6. Then you go through the period 4. You go through the S block, so it's 4s2. And it's something I kind of skipped over is that I'm already saying S2 P6. One nice thing that you get from the periodic table that you don't get from the little diagonal arrow thingy is that the number of groups in each block reminds you how many electrons each subshell can hold. So you got 2 groups in the S subshell. That reminds you that the S's can hold a total of 2. You got a total of 6 groups in the P block to remind you that the P's can hold a total of 6. So when you start going through the D block, remember you drop it down 1. So it's 3D5 or 10. You remember there's 10 because there are 10 groups. 4p6, 5s2, 4d10. I guess I'll just keep going. 5p6. You go through row 6, and again, you go through the S block, 6s2. Here's where we have to remember these two. The F block should be come here right after the S block. So it's 6s followed by 4f. There are 14 groups. That reminds you there are 14 electrons that you can put in the S or F subshell. Then we go back up to 5d10, 6p6, and I don't know if I remember this. See, 7s2. Go down to the F block. Remember it's -2. 5f14. Back up through the D block. 6d10, and then 7p6. So if you go back and look at the filling order that we first talked about, there's your filling order. And it's not only just the order of the subshells. Again, the number of groups reminds you how many electrons are in each subshell. All right, but that's a mess. I'm going to do this later. Actually, it's going to make me delete the table too. Yep, there we go. So another thing that you learn is that, or that's really handy from using the periodic table as a guide to electron configurations, is wherever the atom, its location on the periodic table is, that gives you a hint about what its electron configuration should end at. So, for example, let's look at, say, nitrogen. And if you were going to do nitrogen, you say you already had the filling order in front of you, and you're not using the periodic table as a guide. What you come up with, my pen will come back. Thank you. All right. For nitrogen, you would end up getting 1s2, 2s, 2s2, ugly s, 2p3. That's how its 7 electrons are arranged. But notice nitrogen's in the p block, and it ends in p. It's in period 2. Remember, for the s and p block, it's the period is equal to the, or n is equal to the period. And also, too, notice that if you just look at the p block, nitrogen is in the 1, 2, 3rd group of the p block elements. It ends with p3. And that's true for pretty much the, well, not all of them, but the big majority of the elements. Yeah, its location corresponds with where the configuration should end at. So you look at something like iron. If you work out iron's configuration, it's going to be 1s2, 2s, 2s2, 2p6, 3s2, 3p6. I'll do them slower in a minute. 4s2, 3d6. Again, you'd come up with that just if you just followed, you had the filling order in front of you and you started with 1s and started adding them as you went along. But yeah, notice that, iron ends in D6. It's in the 6th group of the D block. If you just count the D blocks, 1, 2, 3, 4, 5, 6. And it ends in 3D. Remember, to get the filling order, when you go through the D block, you go down 1. So it's in the 4th period of the D block. That tells us it should end in 3D. And it's in the 6th group of the D block, and it ends in D6. So like I said, you can put in all that together, you can figure out the electron configuration of an atom without having to do any kind of rote memorization at all. It's just all you have to do is understand the period, how the two are connected. So, for example, I guess I'll just keep doing it this way. I was going to go down a page. Actually, I don't. I had some. Oh, never mind. I thought I gave myself a lot of blank pages, but I'm still at 1 page. Yeah, page 1 of 1. Never mind. So let's look at, which one do I want to do? We'll look at arsenic. All right. So, and this time we'll use the periodic table, and we'll kind of go through it pretty slow. So arsenic is right here. So it's in the P block. So its configuration should end with something P. And it's in period 4, period 4. And so again, for the S and the P block, when you do the figure out the filling order, in the P block, the end is equal to the period. So that tells us it should end with 4p. And like nitrogen, it's in the 3rd group of the P block, which means it should end with 4p3. So we know that it should end here. Like I said, except for hydrogen, they're all going to start with 1s2, because according to the Aufbau principle, the first 2 electrons are going to go in the lowest, which is 1s. To get everything in between, you just hit row 2 and just work your way down. So when you go through row 2, you're going through, again, the S block and the P block. So, oops. The S block and the P block. And since we're going through period 2, it should be 2S and 2P. And if you can't remember that the S's hold 2 and the P's hold 6, there are 2 groups in the S block. Remind you there are 2 electrons in an S subshell. Likewise, you get 6 groups in the P block. So it should be, it's going to end, you can put up to 6 in the P's. You go through row 3, same thing. You go through the S and the P block, so it's going to be 3s2, 3p6. Now you go through row 4, you go through the S block, and you're in row 4. So again, n equals period for S and P block. So 4s2. Now we go through the D block. Remember, when you go through the D block, you drop down 1 in number, so it's 3D. And since we're going all the way through the D block, we're going through all 10 groups, so it's 3D10. That takes us to row 4 of the P block, and we've already said it ends in 4p3. So that should be the electron configuration of arsenic. So let's look at another example. And this, I'm going to have to do what I did a minute ago. All right. Wasting my virtual board. All right, let's see. Center. All right, so now let's look at, I can scroll down, thank you. We'll look at platinum. Yeah. So platinum is in the D block, so it should end with something D something. It's an ugly D, but who cares? And it's in row 6 or period 6. By the way, this is the same periodic table as the one in the back of my book, on the back cover of my book. So for those of you who use my textbook, if you're not actually in my class at my school, thank you, or thank whoever decided to tell you about it. But also for the current edition, I didn't put the periods in there because I didn't think I'd have room on the back cover. I'm sorry. If I ever do another edition, that'll be in the next one. Actually, I'm starting to think about second edition a lot more than I really want to right now because I don't want to do another edition anytime soon. I just love it, warts and all. But anywho, it's in period 6. Remember, you go through the D block, you know, it's period -1. So we're in period 6, so it should end in 5D since platinum is in period 6. Right, period -1. So it's going to end with 5D something. To figure out that final something, again, the number of electrons is going to match what group it's in the D block. So it's in the 1, 2, 3, 4, 5, 6, 7, 8th group of the D block. And here's a neat little trick. It turns out that the first element in the first transition metal is 21. So if you want to know what group it's in, all you got to do is look at the second number of the very top row. Although it works out for actually all of them with the first one, I guess. But yeah, whenever I want to figure, instead of actually counting, I just look up and go, oh yeah, 8. So platinum's configuration should end with 5D8. It'll let me, I'm outside the tablet zone. You gotta be over here. It's gonna end with 5D8. Again, we know the first two go in 1s2. They all start with 1s2 except hydrogen. So again, we pick up from there, going through row 2. Again, we're going through the S block and the P block. So we're in row 2, so it should be 2s, 2, 2p6. Row 3 is just like row 2. You're going through the S and the P block, 3s2, 3p6. Now we go through period 4. We go through the the S block, so it's 4s2. We're going through the D block, so it'll be drop down 1, 3d10, then 4p6. Got to write smaller. I need room. Now you go through period 5, so it's just like period 4. 5s2. Now you go through the D block, and it's 4d10. Again, D block is -1. And let's see, I'm going to move this down to the bottom. So 4D10, where I'm at 5P6. Now you go through row 6, so you go through the S block. And again, when you go through the last 2 rows, don't forget to go through the F block. And remember, the F block is period -2. So we're in period 6. So that means we're going through 4F. And there are 14 groups to remind us that there are 14 electrons that an F subshell can hold. Now we go back up through the D block. And we've already said it's 5D8. So yeah, the more you practice this kind of stuff, the closer you get to making that connection on how the periodic table is related to electron configuration. And if you keep doing it, eventually you will get to a point where it does finally click. And it's like, oh yeah, I get it. And when you get to that point, pretty much any element on the table, you can predict its electron configuration. What I like to do, I just like to start where it ends and start at 1s2 and just go from there. So yeah, for practice, just pick a number between 1 and 118 and see if you can predict this configuration. Then you can just go to Wikipedia or somewhere and see if you got it right. Although, don't forget, there are these things that we call anomalous configurations. There are a handful. Most of them in the P block, then you get some oddballs like copper. And, you know, my book and most other books kind of mention this as well. There are a few that don't match what you'd predict it to be for other reasons that we don't get into in this course. But by and large, most of them work. And you can usually tell when you have an anomalous configuration because, again, we usually follow the off-bow principle, which says that you start at the lowest and you just work your way up. If it looks like that hasn't been followed, like I mentioned, copper actually ends is, was it 4S1 3D10. So it likes a filled D over a filled S for reasons. And if you see weird stuff like that, where it looks like it kind of went ahead before filling up one before, it's probably anomalous. So just ignore that one and pick another one. But for the most part, what we talk about in this chapter works for the majority of the elements on the table. So yeah, just keep at it, keep practicing, and eventually it'll click, I think. All right, so moving on to General 2. All right, for you guys, we're going to talk a little bit about pH, the pH of salt solutions. And this is something that, you know, teachers, I mean, one trap that I try to not fall into is thinking, you know, why can't they get this stuff? It's because there's stuff, you know, again, I teach this, so it should make sense to me. Otherwise, I want to change careers. But also not write a 2-volume book on the subject. But I'm always surprised about how challenging it can be sometimes to figure out salt solutions. So we're going to talk about our pH of salt solutions. Because of all the stuff that we talk about, like ice-table stuff and some of the electrochem stuff we talk about later, the pH of salt solutions tends to stand out the most. And I don't know, I'm not saying that, you know, why aren't they getting this stuff? Yeah, I'm always surprised that that's one of the things that kind of gets people, because it's very qualitative. I mean, there's no math really, as far as identifying what type of salt you're dealing with. But anyway, we'll go over it a little bit. We got time. So wait, where I'm at, there we go. Let's go back to Word and get rid of all that. So usually after talking about acids and bases, we'll start to talk about how pH isn't just affected by what you think of as an acid or what's usually thought of as a base. Any compound can really affect, has the potential to affect a solution's acidity, even though you don't traditionally think of it as an acid or a base. And in General 2, we kind of limit that talk to salts for the most part. You might learn about a few more if you move on to organic. But if you take a compound like sodium fluoride, get sodium's an ionic compound, or sodium fluoride is an ionic compound. It's made up of sodium ion and a fluoride ion. So for reasons that I don't have time to talk about, but the book mentions it, goes into a little bit. Group 1A and 2A ions, they usually what we call neutral ions. They don't react with water at any significant degree. There's no Bronsted acidity or basicity with water for reasons. So it's neutral in water. It's not going to react with water. It's not going to accept a proton. And doesn't have any to donate. So, although I guess we'll see later for group 3A, that doesn't matter. But yeah, for group 1 and group 2A compounds, I guess except beryllium. Group 1 and 2A cations don't show any significant acidity or basicity in water. The basicity rollers. So they're neutral. But fluoride is the conjugate of a weak acid. It's the conjugate of hydrofluoric acid. So remember, the conjugate of weak acids can act like bases. A fluoride ion can react with water like a Bronsted base, accept that proton to give you HF and hydroxide. All right. So notice that one of the products we're getting is hydroxide. Also, we just said fluoride is accepting a proton. So fluoride is a basic substance. When fluoride is present in water, it will act like a Bronsted base, which means overall, you have an ion that's not reacting with water, one that is acting like a base. Sodium fluoride is an example of a basic salt. So if you put that compound and put it in water, the pH is going to go up. Right. So on the other hand, you look at an example like, which one do I want to use? Ammonium chloride. So just take it one ion at a time. All right, we'll look at ammonium first, and then we'll think about chloride for a second. Actually, in this case, I'm going to do chloride first. So in the case of chloride is the conjugate of HCl, hydrochloric acid. So that's a strong acid. So remember, you take a strong acid and you put it in water. Strong acids essentially react completely. There's no significant equilibrium. All right, so that means the reverse isn't happening to any significant degree. So you take chloride and you put it in water. Chloride can't act like a Bronsted base, chloride can't act like a Bronsted base like fluoride can. Nothing's going to happen. So yeah, chloride is a neutral ion. Right? It doesn't show any acidity or basicity with water. But ammonium is the conjugate of ammonia, which is a weak base. So again, if you're the conjugate of a weak acid or base can act like acid or base. Conjugates of weak acids can act like a base. So they're usually called conjugate bases. Ammonium is the conjugate acid of ammonia. So if the conjugate or weak conjugate pairs can both show Bronsted-Lowry acid-base behavior. So ammonia usually acts like an acid. So ammonium is conjugate. Again, ammonium is the conjugate acid of ammonia. So yeah, it can behave as a Bronsted acid, oops, donate a proton to water to give you ammonia and hydronium. All right. So yeah, ammonium is an acidic substance. You put it in water, it's going to cause the pH to go down. So one ion is acidic, the other ion does nothing. So overall, ammonium chloride is an acidic salt. Look at another example. Let's look at sodium chloride, which is made up of sodium ion and chloride ion. So a minute ago, we said you put sodium ion in water. It does nothing. It's neutral. All right, you put chloride ion in water. It does nothing. It's neutral. So neither ion does nothing. I did mention I was Southern earlier, right? So this is an example of a neutral salt because neither ion reacts with water to any significant degree. Let's see, I guess there's, of these four ions, there's another combination you can do, which is ammonium fluoride, which is made up of ammonium ion and fluoride ion. So a minute ago, we said that ammonium is an acidic ion. And fluoride is a basic ion. Now, your first instinct may be to say, okay, one's an acid, one's a base, they're going to cancel each other out. They're neutral. But remember, one's a weak acid, one's a weak base. There's a reversibility equilibrium thing going on. So that it'd only be neutral if they both produce the same amounts of hydronium and hydroxide. The way to kind of gauge if that's the case is to look at the Ka of the acidic one and the Kb of the basic one. Ammonium, got to move something. Ammonium has a Ka of 5.6 times 10 to the negative 10. Fluoride has a Kb of 1.4 times 10 to the negative 11. So they're both pretty small, but the Ka of our acid is a little bit bigger than the Kb of our base. When that's the case, you have an acidic salt overall. If it was the opposite, if the Kb was the bigger of the two, you'd predict the salt would be basic. And if they happen to be the same value, then they would be neutral. So, overall, it kind of looks like this. Not that. No. Last page. Do a new page. You won't let me do it. There we go. Thank you. So, again, you take it one ion at a time. All right. You look at the cation, and you look at the anion. With the cation, there are kind of two main scenarios. One, the cation, well, actually, I guess three. Four, no one expects the Spanish equals. Anyway, actually, I'm going to give myself a little more room here. There you go. The anion over here a bit. So again, if the cation is a group 1A or a 2A ion, except beryllium, but you don't see beryllium a lot in Gen 2. Those cations are generally neutral. Now, we didn't have time to talk about it today, but if you have to know this, your book goes into it a little bit more, like mine. But for any others, actually, whoops. And 11 weeks, I still can't get the hang of this stupid tablet. All right. That's our, yeah, Yeah, I keep moving my hand, and I don't know. Can't figure out a way to fix that. Anybody who works at Wacom, let me know. But yeah, if it's a group 1A or 2A cation, it's neutral. Anything else, all others, tend to be acidic ions. That includes any other metal ion like group 3 or transition metals, or things like ammonium. So, and if it's group 1A or 2A, except beryllium's a little acidic, it's neutral. If it's not one of those two groups, you're predicted to be acidic. For the anion, if it's conjugate, HA, just slap a hydrogen on that. If it's strong, conjugate strong, then it's going to be neutral. If it's weak, if the conjugate is a weak acid, that means A minus can act like a base. So again, those are the I guess the 4, I can't count, areas you kind of look at. So you look at each ion individually and see what each one does. Then you put the two together. If one of the ions is neutral and the other isn't, it's just whatever the other one, non-neutral one, does that determines the acidity or basicity of the salt. If both of them are neutral, then yeah, it's a neutral salt because neither ion's doing anything. If one is acidic and one is basic, then you compare the Kas. There's actually another one you may see. It usually happens with the anion. There are some cases where the anion may be amphoteric. For example, I think the one I use in the book is H2PO4 minus. It could either donate a proton to become hydrogen phosphate, or it could accept a proton to become phosphoric acid. And usually in a solution, it's doing both. But to see which one it's better at, compare the Ka of that ion with the Kb of that ion. Whichever one is bigger, it's just like the last case we looked at. If its Ka is bigger, it means it's a better acid, which means it's going to be an acidic ion. If Kb is bigger, it's going to be a basic ion most of the time, which means the Kb, or it means the I can't switch screens and talk at the same time apparently, which means the it's going to be a basic ion. So yeah, that's the best advice I can give you if you're kind of stuck with figuring out salt pH. Just first thing, take it one ion at a time. All right, so what does this one do, and what does this? Then look at the other one and see what that one does. That one do. Me no talk no good today. Ever really. I'm a better writer than I am speaker. I don't know. I do all right in class. Kinda. Yeah, look at the two ions individually. Again, there are usually 4 main categories. Every now and then you get an amphoteric ion, but usually it's most of the time, one's going to do something and the other is going to be neutral. In that case, you look at the one that does something. That'll dictate what type of salt it is. If they're both neutral, then it's neutral overall. If they both do something, it's usually a case where one's acidic and one's basic, because of the way Bronsted-Lowry chemistry works. If that's the case, again, just compare the Ka of the acidic one, which is usually the cation, and the Kb of the basic one, which is usually the anion. Whichever one bigger. I really can't talk today, can I? Whichever one bigger wins. Like I said, you might see an amphoteric ion. It's just like that last case I mentioned. Whichever K is bigger is the one that's going to be the most. All right, so that's it for today. Happy spring holiday, college holiday, spring break, or I don't know, happy Saturday if you're not watching this the week I'm recording it. Merry Christmas. No, you wouldn't be watching it during Christmas. I don't think too many people are on quarters anymore. I don't know. Happy winter quarter. But anyway, that's it for today. Next week, I'll do something else. Yeah, I'm going to try to not say what I'm doing because I might change my mind. But if you're watching this before it goes live, just let me know in the comments or shoot me an email. And I will think about adding it to the show. No promises. Yeah, we'll see. It helped me greatly if I get feedback. Positive feedback. Negative feedback, just there are other places on the internet you can give me that. But that's it for today. Job's done.